Okay, so let's record. Let's go over the acids and bases. So here are questions specifically on naming acids or writing the formula out. So we looked at hydroiodic right here, HI. Sulfuric acid is H2SO4. Phosphoric acid is H3PO4. Hydrosulfuric acid, H2S. So remember, your binary acids are the ones that just have hydrogen and one negatively charged element in it, you can see, right? Whether it be iodine or sulfur, in this case. Okay, so the next one is H2CO3. So CO3 you should recognize as carbonate. So then this would be an oxy acid. So there's no hydro in front. This is actually something called carbonic acid. All right. H3P would be hydro. This is binary. There's only two things in it. Phosphoric acid. All right. Whereas phosphoric acid, you see, is hydrogen with phosphate. All right. HClO3 is chloric acid. Okay, there's your oxy acid. HF would be hydrofluoric acid. And HNO3, you can recognize the polyatomic, that is nitrate. So that would be nitric acid. Okay, so there's your two types of acids, the binary and the oxy acids. Okay, we already did these, so I think, well, maybe we didn't do these. Did we do these? Maybe we did, huh? Did we do, I can't remember if we did. Did we do these ones last time, girls? Do you remember? We covered these? I think we did.
Yes.
Yeah, we did. Okay, so we don't need to cover these ones. But here are some further practice ones. So some of them are just repeats, like chloric acid. We just saw chloric acid. Chloric acid was HClO3. Lithium hydroxide would be LiOH. Lithium is +1, hydroxide is -1, so one of each. We already did carbonic acid, so that would be HTCO3. We did hydrosulfuric acid, so a lot of these are repeats actually. Hydrosulfuric is H2S. We did sulfuric already, so sulfuric is H2SO4. Strontium hydroxide. Strontium is, where is strontium on my periodic table? Let's see. I think strontium is +2, but I'm not 100% sure. Let's look it up. Strontium is atomic number 38. So where is that in the periodic table? It's in the second row, so it's +2. So I don't know if you can see that on my screen. It's highlighted right here. There's right there, number 38. So if you remember your patterns from chemistry, row 1 is +1, row 2 is +2. So strontium hydroxide should be SrOH2, because if this is +2 and that's -1, crossover rule predicts SrOH2. Phosphoric acid is, we did this one already, H3PO4. Hydroselenic acid, so we have to look for selenium. Where is selenium? Let's look up selenium. Let's see, periodic table. Oops. See what comes up. All right. I don't mind Wikipedia. Wikipedia is fine. Says it's atomic number 34. You can see where it is. It's in the So it's not the last row. Last row would be your noble gases. It's not the second last row. Those would be negatively charged, -1. It's in the third last row. So that would be -2. So selenium would be negative, sorry. Selenium, Se, is -2. So that would be H2SE. Okay. Nitric acid, we did that one already. That's HNO3. And magnesium hydroxide, magnesium is +2, hydroxide is -1. So that means we need 2 hydroxide. All right. And then the other ones you have the formula, and then you got to come up with the name. So this is AU is gold. So gold is a transitional metal. If you look up where gold is in the periodic table, gold comes up as a transitional, right? Gold is a transitional metal. So we know that means that it has more than one charge. So it's saying that's AuOH. So we know hydroxide is -1, which means gold has to be +1. So this will be gold 1 hydroxide. Okay. H3PO4, we know what that is. That's phosphoric acid. Okay. The next one is calcium hydroxide. The one below that is copper. Copper is also a transitional metal, so that would be copper 1, because just like this one, there's only one hydroxide, so it means copper is +1. HBr, it's binary, so we know we have to write hydrobromic acid. We know what H2CO3 is now. We know that's carbonic acid. So there's a lot of repeat here. I apologize. TE is tellurium, I believe. Don't have periodic table memorized, but I should have it memorized. It's just tellurium, not tellurium. So it's, there it is. So its name should be hydrotelluric acid. FeOH2, so that would should be iron 2 hydroxide, because if I go crossover rule in reverse, that means the iron was +2. HClO3 we know is chloric acid from before. We've done that one a few times now. Oh, I'm going blank here. Okay, and the last one is beryllium hydroxide. Beryllium is not transitional. Okay, what happened to my chloric acid? All right, so that's it, I think, for naming acids and bases. Okay, any questions about that? Okay, so then let's move on to today's topic, because today we're actually going to talk about, I mean, this is all about naming acids and bases, but today I actually want to go over what is an acid and what is a base. So I posted this document. I think I sent you a notification that I posted it. So I am recording this. If you don't have this document with you right now, you can always get it after, and then just fill in whatever information that you need to fill in. We're going to talk today about what an acid and base is. We've talked about naming them. We've talked about the formula for acid and bases, but what exactly is an acid and base? Okay, that's what we're going to go over today. So an acid, if you notice that every equation that we did for an acid there's always the letter H in front of it, right? Whether it's carbonic acid, whether it's hydrochloric acid, whether it's sulfuric acid, there's always the H in front. Because what an acid is an acid that is something that releases protons. If you remember, I said to you that there's usually this little symbol that identifies it as an acid. Otherwise, you could just say that this is hydrogen chloride. But in water, what happens is that the acid actually splits up. So HCl actually becomes a proton and a chloride ion. Carbonic acid actually becomes 2 protons and carbonate. Sulfuric acid actually in water becomes 2 protons and sulfate. So if you notice, in water, they all do the same thing. They all release protons. That's the definition of an acid. Okay, an acid is something that releases protons. Hydroxides, on the other hand, are things that either remove protons or release hydroxide. Now, all the examples that we've done so far are things that have hydroxide in them. All the bases have hydroxide, right? So for instance, like potassium hydroxide, if you put that in water, what it does is it splits into potassium and hydroxide. So there you see it's releasing the hydroxide. If we put calcium hydroxide in water, that little AQ symbol, then what happens is the calcium releases hydroxide also, but it just releases 2 of them, okay? So there's a huge difference right there between bases and acids in terms of what they release. However, not all bases have hydroxide in them. Sodium bicarbonate, which is this one right here, this is baking soda, okay? Baking soda is a base. It's considered a base because bases can also, they don't have to just release hydroxide. They can just simply remove hydrogen. So for instance, baking soda, if I look at baking soda, I don't see hydroxide in the formula, right? There is no hydroxide in there. But I know that HCl will split up and it forms hydrogen ions and chloride. So what happens is the sodium bicarbonate actually removes the hydrogen ions when it reacts with the hydrochloric acid. Because if I look on the right side of the equation, you'll notice that I have salt, sodium chloride, I have carbon dioxide, and I have water, but I don't see the hydrogen ions. The hydrogen ions have been eliminated because they've actually been neutralized by my baking soda. So the key point here is not all bases have hydroxide. Their job is to either release hydroxide or remove the protons. That's their job, okay? So just keep that in mind. Not all bases have hydroxide in them. All right. Okay, so we know what an acid is something that releases protons. A base is something that releases hydroxide or removes hydrogen ions, okay? There is a really important scale that allows us to classify these things. That's the pH scale. The pH scale is actually, normally you see a scale from 1 to 14, but can actually go below 1. So you can get pHs of 0, you can get negative pHs, but it doesn't really matter for grade 10. We're just going to understand what the scale means, okay? So when you have a scale that says, or when you have something that has a pH of 7, what that means is neutral. So it's not an acid and it's not a base. It's neither one of these two things. It's neutral. If it's below 7, then it's acidic. If it's above 7, then it's basic. So for example, milk is acidic. For some reason, an egg is basic, okay? Tomato juice is acidic. Bleach is basic, all right? The scale, not only does it tell you if it's acidic or basic, it also tells you the relative strength. So for example, as we go this way, the acid actually gets stronger. And as we go this way, the base gets stronger. Okay, so in other words, as we move away from 7 in either direction, the solution becomes either a stronger acid if it goes down away from 7, right? 7, 6, 5, 4, 3, all the way down. It becomes a stronger acid. And as we go up the scale, it becomes a stronger base. Okay? I'm going to show you how to read it. You can do a little bit of simple math with it. In grade 11, you'll do some more complicated math with it. But in grade 10, we can do some basic stuff with it. The scale is called a negative logarithmic scale. Now, I don't know if you do logarithms in grade 10. I would imagine you don't do it. So we're going to keep this simple. What this means is that the scale goes up by factors of 10. So every time we go up the scale, we increase the value by 10. So for example, if this is 1, then one step up the scale would be 10. The next step up would be 100, and then it would be 1,000, and then it would be 10,000, and then it would be 100,000. So what that means then is when we go from, like, for instance, pH 6 here to pH 5, and we're going down a step, we're not going down, like, it's not saying that black coffee is just like, I don't know, 1 time or 2 times weaker than milk, or 3. It's actually saying black coffee is 10 times weaker than milk, according to this scale. Because every step in my scale represents a change of a factor of 10, okay? So knowing that, we can actually do some really, really simple math to compare acids and bases. Well, we're gonna just look at acids as our examples, but it would be also true for bases, okay? So here's the unit, which you don't need to know. You'll learn more about this in grade 11, okay? But if you're curious, the unit is something called moles per liter, all right? It would be like, you know, the unit for mass is kilograms, the unit for speed is meters per second, something like that. And this is what a mole is. But again, you'll learn about that in grade 11. The key point here is how to compare values on that scale, all right? Now, I mentioned the scale is a negative logarithmic scale, okay? So what that means is this. If I have something on the scale that is, for instance, a pH of 4, let's say it has a pH of 4, okay? That would mean that you would write it as 10 to the negative 4, okay? A negative logarithmic scale. You'll notice it is a negative value, okay? pH of 6 would be 10 to the negative 6, all right? pH of 2 would be 10 to the negative 2. And it doesn't have to be a whole number. I mean, there's no reason why you can't have, for instance, pH 1.5, and then the, sorry, the screen just froze again. Then it would be written as 10 to the minus 1.5, okay? But because you haven't done logarithms before, then we're just going to stick to whole numbers, okay? Just to keep it really, really simple. Okay, so like I said before, if it has a pH of 7, that means you write it as 10 to the negative 7, okay? And this, by the way, is the amount of hydrogen. We're talking about the amount of hydrogen. There is also something called a pOH scale, which is actually, if the pH scale measures the amount of hydrogen, then the pOH scale measures the amount, obviously, of hydroxide, okay? But you'll learn more about that in grade 11 chemistry, okay, if you take it. What I can show you here, so first off, if it's a pH of 7, that means that's not acidic, it's not basic. Actually, at these 2 points, the pH and the pOH are actually the same. Okay, but I'm going to show you how you can use the pH scale to answer questions like how many times stronger is this acidic solution compared to this other one. Okay, so we know it's a negative logarithmic scale. So for example, if I have a solution that is a pH of 3, okay, I would write it as 10 to the negative 3, as I showed you before, right? And if a solution is pH 5, I would write it as 10 to the negative 5. Now, what that means then is if I compare these two solutions, 10 to the negative 3 versus 10 to the negative 5, then the math says that the solution as pH 3 would be 100 times stronger because, and I think you do this in grade 9 or 10 math. I'm not 100% sure. I think you do. When you divide 10 to the negative 3 by 10 to the negative 5, when you divide exponents, you subtract them. Okay? So you notice at the same base, 10 and 10. So when I subtract the exponents, it would be negative 3 minus negative 5, which adds to plus 2. Okay? So the 10 to the negative 3 divided by 10 to the negative 5 would be 10 to the power of 2. Now, 10 to the power of 2 is 100. Okay? This is how you use the scale to figure out how many times stronger or weaker, you can do it the other way around, one solution is compared to another. So let's look at an example, which I thought I had here. So let's make an example then. Let's compare pH 5 versus pH 1. Okay? Now, pH 5 and 1 are both acidic, but if you recall, as we move from 7 down, it becomes a stronger acid. So what that means then is that pH 1 is the stronger acid. So if I said to you how many times stronger is, or how many times more acidic is a pH 1 solution, right? So for instance, maybe something like, it says gastric acid is pH 1, but I always thought it was pH 2. But let's just go with the scale. I think it's actually pH 2. Compared to like black coffee, which is pH 5, okay? So then, it says that the scale is negative logarithmic. So that means the pH 1 is pH would be written as 10 to the negative 1, right? Whereas pH 5 would be written as 10 to the negative 5. So now if I divide 10 to the negative 1 by 10 to the negative 5, I subtract the exponents. So negative 1 minus negative 5 is positive 4, which means my answer is 10 to the power of 4. 10 to the power of 4 is 10,000. So pH 1 is 10,000 times more acidic than pH 5. We can also just say pH 5 is 10 to the 4 times weaker, or 10,000 times weaker than pH 1. This is true too, right? Okay. pH is actually quite important to biology. Your blood pH is around 7.3 to 7.45. So you can see that it's actually slightly basic. You actually don't want it to be lower, or either lower than that value or higher than that value. That actually could be dangerous, maybe even fatal. All right. We know that some organisms that you probably, I don't know if you studied this yet, but I think you might do it. Maybe in climate change, talk about like the coral reefs and how sensitive they are to environmental change. So we know that some organisms are very sensitive to pH changes. One such case are the coral reefs. And the reason is because their skeleton's made up of something called calcium carbonate. And what happens is the calcium carbonate actually reacts with the acid to sort of dissolve and weaken the what's called the exoskeleton. And that actually is very, very bad for the coral reefs. And the coral reefs are actually very, very productive. So that would be very catastrophic for not only the reefs, but anything that uses the reefs. But here's the question. Why would the pH drop in the oceans? If a drop in pH is really bad for the coral reefs, okay, it's really, really, sorry, that's not the question. The question is, what would cause the drop in the pH? We know it's bad. It's not if it's bad. We know it's bad, but why is that happening? And it turns out that one major pollutant is CO2, which is ironically has been reduced in the last month or so because of this viral outbreak. So one good thing about this viral outbreak is actually pollution's gone down, but definitely CO2 levels have increased over the last, several hundred years. So what happens is the high levels of the CO2 react with water to form something called carbonic acid. And the carbonic acid then would lower the pH of the ocean, and the drop in pH affects the exoskeleton, which is made of calcium carbonate of coral reefs. And I mean, so you can see it here, it's carbon dioxide reacting with water. This is the issue. That's why the pH actually drops. Another thing that could be produced from pollution is sulfur dioxide. But sulfur dioxide can also just simply be produced from volcanoes. So volcanoes can shoot out sulfur dioxide. And what's really cool about this next example, here's a picture of a lake in Indonesia. This lake is the result of basically sulfur dioxide from volcanoes mixing with water. So just like we just saw with carbon dioxide and water forming carbonic acid, sulfur dioxide and water, so water and sulfur dioxide, actually form sulfuric acid. That's actually not balanced. We must be missing something here. I think there's, hold on. Obviously this is not balanced, so I need to check in on that. Why is it, maybe this is not the complete reaction. This might not be the complete reaction. I'll have to look into that. But there's a reaction between sulfur dioxide and water to form sulfuric acid, because this actually would be, this would be sulfurous acid, SO3. So I'll have to look back into that. But this, so the sulfuric acid is actually produced from the sulfur dioxide in the water, actually produce a lake that is so acidic that it's more acidic than your stomach. In fact, you know, the scale said that the stomach acid was about 1. It's actually 2. It should be 2, from what I remember. This lake has a pH of about 0.5. So if we go back to what we were doing before, that would mean that the lake would be, if you did the math, you do the negative logarithm, right? So 10 to the negative 0.5 or 10 to the negative 2 would give you an answer of about 10 to the power of 1.5. Because remember, it's negative 0.5 minus negative 2 would mean positive 1.5. So the answer is 10 to the power of 1.5. So you don't need to know, I mean, we're not going to do anything that's not a whole number, but just so you know, 10 to the power of 1.5 is, let me just punch it in my calculator, is actually about 32. It's about 32 times stronger than the acid that's coming out of, that's in your stomach. So you definitely don't want to be swimming in this lake. You would not survive. You would just dissolve. We've already talked about neutralization reactions before. So we've done a little bit already on acids and bases, and we talked about neutralization reactions. If you remember, it was an example of a type of reaction. So just to refresh your memory, we just said that your stomach is acidic. What's interesting though is the stomach empties into something called the small intestine, which is actually basic. So the question is, what type of chemical is released to deal with the contents of the stomach as they empty into the small intestine? Well, the answer is it has to be obviously a base, because the stuff coming out of the stomach is acidic, and the environment of the intestine is basic. So it's obviously got to be a base to neutralize the acid. In fact, the base is sodium bicarbonate. It's actually baking soda. Interesting little fact. Okay, so we have done some neutralizations. I don't think we did too many of them, but just to refresh your memory, what it is, it's a reaction between an acid and a base that gives you water plus some ionic compound called a salt, which you can see here. Water, and there's your salt. Water, and there's your salt. So there's your acid, there's your base, there's your acid, there's your base. And you can see the products, the water and the salt, all right? Here are just some practice questions. So for instance, how many times more acidic is pH 2 relative to 6? We actually did that one. pH 2 is 10 to the negative 2. pH 6 is 10 to the negative 6. So negative 2 minus negative 6 is positive 4. So that's 10 to the power of 4. So that would be 10,000 times more acidic. pH 1.5 versus 5 would be 10 to the negative 1.5 over 10 to the 5, negative 5. So that is 10 to the 3.5. Now, you won't get any, if you do come across these on your online, there won't be any, they're just going to be whole numbers. So you won't have to worry about any decimal values. But just so you're aware, you can have decimal values, and this works out to about 362 times stronger. If you are curious, because I don't know if you're familiar with this sort of stuff, the way you would do that is 10 to the 3.5 would be 10 to the power of, so you put the little exponent to the power of 3.5, and there is the answer. So 3,162. So once again, that's 10 to the power of, see, x to the power of y to the power of 3.5. There's your answer. But again, you're not going to come across any. You're only going to come across whole number values in your online quiz, okay, or online test, whatever you want to call it. Okay. Sorry, last thing. Oh, there's one more. pH 3.3 versus 6. Again, you're not going to come across anything that's other than whole numbers, but just to do it, pH 3. Sorry, I don't know why it does that. It just jumps around sometimes. Okay, so 10 to the negative 3.3, right? Divided by 10 to the negative 6.6. So negative 3.3 minus negative 6.6 would be positive 3.3. So again, 10 to the power of 3.3 is 1,995. So that's 10 to the power of 3.3, which is 1,995. But one more time, your online quiz, you're only going to have whole numbers to deal with, so it'll be much easier to work with, okay? And just to recap, because we've done some of these, neutralization reactions, let's just look at two. So ammonium hydroxide and nitric acid. So ammonium hydroxide and nitric acid. So you're going to get water and you're going to get ammonium nitrate. If you remember, sometimes we classify these as like double displacement reactions because it seems like that's what's actually happening. Partners are switching. And I think this is actually balanced. I think it is balanced. It is balanced. Okay. And then the other one is potassium hydroxide and hydrosulfuric, not sulfuric, but hydrosulfuric acid react to form water and potassium sulfide. So we can see that this one is not balanced. So we would need 2 water molecules to balance it. Okay, I think that is it. So one more time, some of these things, these concepts on acids and bases will be on the online test. I tried to keep the questions as simple, but just fair warning, some of them are a little bit tricky, so make sure that you really read the questions carefully, because sometimes the difference between like sulfate, versus sulfite, if you're not paying attention, you might not notice there is a difference between those two things, right? So just be careful when you read the questions, because one little letter can be the difference between you getting something right, something wrong. All right? Let me stop the recording, and then I'll take any questions.